Welcome back to my YouTube channel. In this video, I am going to discuss about potential energy of a dipole in a uniform magnetic field. Magnetic dipole means a north pole and a south pole separated by a small distance. If you consider as a bar magnet, the north and south pole is separated by a small distance. So we can consider the bar magnet as a magnetic dipole. If plus Qm is the pole strength of the north pole and the minus Qm is the pole strength of the south pole, and the separation between them is 2m, then the magnetic dipole moment of this is Qm into 2l. What about the direction of magnetic moment? That is the direction of the 2l itself. That is the 2l direction we are taken from the south to north like this. This is the magnetic dipole moment direction. Okay. This dipole I am going to place in a uniform magnetic field. You see this in this region, and consider the magnetic field is uniform. That is, the magnetic field value is B. Okay, a dipole I am going to place like this. Here is the south pole and here is the north pole. Okay, so I am placing the dipole in such a way that the dipole moment M and the magnetic field B is making an angle theta. So we know if a dipole is placed in a magnetic field, it will experience a torque. So the torque is mp sin theta. Okay, but the net force is acting on it is 0. Okay, so this dipole also will experience a torque. In which direction? Like this, it will experience a torque. So due to this torque, the dipole started to rotate in this direction. Okay, if you apply a force on an object, it got a displacement, we can say that there is a work is done. If a torque is acting on a body, got a rotation or got a angular displacement, we can say that there is a work is done. So here you see this. There is a torque is acting on the dipole and the dipole got a rotation. That is an angular displacement. So there is a work is done. This work done is stored as the potential energy in the dipole. Okay. So if due to this torque there is a small displacement, that is angular displacement, got this dipole. If so that the small work done, that is the torque is equal to tau d theta. Okay, small work done due to the small angular displacement d theta. Okay, if the dipole is rotated from theta I to theta f, then the total work done is the integration of theta I to theta f dw. Okay, then what is dw? That is theta I to theta f tau d theta. Okay, so what about the torque value? Theta I to theta f this is mp sin theta d theta. Okay, mp is a constant, you can take it outside. So mp into theta I to theta f sin theta d theta. Okay, sin theta d theta. What is the integration of sin theta? The integration of sin theta is minus cos theta. Okay, so we'll get the work done. This work done is stored as the potential energy. That is, work done is equal to potential energy. That is equal to mp into the integration of minus cos theta. The lower limit is theta I and the upper limit is theta f. I am taking the minus outside and applying the upper and lower limit. So we will get cos theta f minus cos theta I. This is the potential energy possessed by a dipole when it is rotated from theta I to theta f. If we will consider zero potential energy point is the reference point, then theta I we can take it as 90 degree and theta f is equal to theta. That means initially the angle between the dipole and the magnetic field is 90 degree. That is, the dipole is like this. The dipole is placed like this. Okay. So then after that it is rotated theta. Okay. So now we will see the potential energy is equal to minus NB cos theta minus cos 90 value, that is 0. So from this, potential energy is equal to MP cos theta we will get. This is the potential energy possessed by a dipole when it is making an angle theta with the magnetic field. Okay. Then this dipole here I am taken in the bar magnet shape. It is not necessarily like that. You can draw this dipole in the magnetic needle shape also you can draw. Okay. Now we will discuss some special cases. That is a case 1. Case 1, I consider theta is equal to 0. Theta equal to 0 means, look at the diagram, how the dipole. Okay, so this is the dipole, this is the south pole and this is the north. This is the magnetic moment direction and the B direction is, this is the B direction. Now you see the magnetic moment and B are in the same direction, so that the theta is 0. What about the force acting on it? The net force is 0 because the magnetic field is uniform. What about the torque? The torque is mb sin theta. Here sin theta is sin 0, so this is also 0. Okay, so force is 0, torque is 0, this dipole is in equilibrium. We'll check about the potential energy, that is minus mb cos 0, that is, we'll get it as minus mb. That is, potential energy is negative, that is, the energy is the minimum, that is the minimum energy we are getting. Okay, so now you see, in this dipole, the net force is 0, net torque is 0, and the potential energy possessed by the dipole is minimum. Okay, so we can say that this is the most stable position of the dipole. Okay, most stable position, or we can say that the dipole is in stable equilibrium, or we can say that dipole is in stable equilibrium. So if a dipole is in stable equilibrium, the angle between the magnetic moment and magnetic field is 0. Okay, this is the case 1. Now we will discuss the case 2. Case 2, if theta is equal to 180 degree, how theta become 180 degree? The magnetic field is like this direction, the dipole is like this, that is, the south is here, north is here, the magnetic moment direction is like this. Now you see that the magnetic moment the magnetic field are in the opposite direction. So what about the net force? Net force is 0. And what about the torque? Torque is equal to mb sin theta, that is sin 180. Sin 180 also 0. So this dipole, the force is 0 and the torque is 0. So this dipole is in equilibrium. What about the potential energy? That is minus mb cos 180. Cos 180 value minus 1. So we are getting plus mv. That is the potential energy is positive. The potential energy is positive. That is the maximum value. That is the maximum energy. So you see this dipole is possessing the maximum energy. So this is the most unstable position. So this is the most unstable position. Unstable position. Or we can say that this dipole is in unstable equilibrium. Unstable equilibrium. So if a dipole is in unstable equilibrium, the angle between the magnetic dipole moment and B is 180 degree. Okay. This is about the potential energy possessed by a magnetic dipole.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like and share.